In this video, we are continuing section 6.3 on the unit circle, and we'll get into what the unit circle is and how we use it. So we've used SOHCAHTOA before to get trig functions, to define trig functions when our angle was in a right triangle. So if I had a right triangle, and I had some angle theta in it, then we had formulas for defining trig functions. So in that context, theta has to be something between 0 and 90 degrees. My goal now is, can we extend those definitions of trig functions so that they work when our angle is bigger than 90 degrees, and also when our angle is negative, if it's less than 0 degrees. Okay, and this is where we are going to use something called the unit circle. So I'm going to draw some axes. Then I'm going to draw a circle centered at the origin. And the word unit means 1, like length 1. So in this context, that means the radius of the circle is going to be 1. The radius of that circle is going to be 1. So I'm going to label these values here. That's -1 on the x-axis. This is -1 on the y-axis. And now I'm going to draw some point on the unit circle. Some point, I'll label this x comma y. And then I'm going to connect that point with the origin. I'm going to connect that point with the origin. And when I do that, the angle from this positive x-axis measured to that line segment, that radius, I'm going to call that theta. Okay, so because it's a unit circle, this length of this radius is 1. Okay, so theta here could be, if my point was like up here, I would be measuring then a 90-degree angle from the positive x-axis. But it could go even bigger than that. Like if my point was somewhere over here, then we'd be talking about an angle that's bigger than 90 degrees. Okay. All right, so now from this point x comma y, let me drop a perpendicular line straight down to the x-axis. A perpendicular line. So when I do that, it creates this right triangle. In fact, this length right here is my x-coordinate, and this vertical length right here, that's my y-coordinate. Everything here is positive because this point x comma y that I've drawn, it's in the first quadrant. So the x and the y are going to be positive. Okay, so what I'm going to do is I'm going to use SOHCAHTOA to say what the trig functions are. So using SOHCAHTOA in this picture, sine is equal to the opposite, which is y, over the hypotenuse, which is 1. And that just simplifies to y. Okay. And what I'm going to do is I'm going to use this definition even when my angle is something bigger than 90. So even if my theta was like this big, I'm going to be using whatever this point's y-coordinate is to define what sine is. Sine is going to be the y-coordinate of my point. Okay. So same thing for cosine. Cosine using SOHCAHTOA is adjacent over hypotenuse, x over 1, and that simplifies to just x. So that's what cosine of theta is going to be, no matter where this point is in our unit circle. Tangent using SOHCAHTOA is opposite over adjacent, y over x. So y over x. And then the other three trig functions are the reciprocals of these. So cosecant is 1 over y, secant is 1 over x. And then cotangent, that is x over y. So I'm going to box these. So these are the definitions of our 6 trig functions, but now in the unit circle. So these definitions, they match what we expect with SOHCAHTOA as long as this point is somewhere in this first quadrant. That means if my angle is something between 0 and 90, these trig definitions match exactly what SOHCAHTOA says. But it just lets us be more general. Now it lets us define trig functions even when our angle is somewhere over here in quadrant 2 or quadrant 3 or quadrant 4. I can define trig functions. Okay. All right. So one of the things that we'll need is be able to figure out trig functions at a bunch of different angles. So this is where the labeling the unit circle is going to come into play here. So I got this blank unit circle. And I'm going to label first a bunch of angles in the unit circle, and then we're going to think about, well, what are their x and y coordinates? Because I'll need the x and y coordinates so I can plug in and figure out sine and cosine and tangent. Okay, so remember that when I go from the origin to this positive x-axis over here, to the positive x-axis, well, that's 0 degrees. That's what we consider 0 degrees. That's 0, and then this symbol here is a degree symbol. That's 0 degrees. And if I were to go all the way around, and make a full circle, well, that's also 360 degrees. So that's 0 degrees, and comma, that is also 360 degrees. 360 degrees is also there. Okay. This next angle is going to be 30 degrees. 30 is something that's simple enough for us to figure out coordinates using our 30, 60, 90 triangles, and we'll do that in a sec. The next angle is going to be 45. 45 is also a nice angle I can do stuff with. The next angle is going to be 60. I can also do nice stuff with that. So notice my special triangles are going to be used here, 30, 60, 90, and 45, 45, 90. So just to get me ready with those, I'm going to draw a couple of those on the side. Okay, so this first one is going to be where this angle is 30. And if that angle is 30, this one's 60. And this is a unit circle, which means that radius, this radius here, that is like the hypotenuse of a right triangle like this. So that hypotenuse is going to be 1. And that next triangle I was looking at is if this radius is like this, making this 45 degree angle. So if I'm making a 45 degree angle like that, I'm going to get a 45, 45, 90 triangle. Let's draw one of those. So 45, 45, 90. Okay, so this is going to give me a 45, 45, 90. And again, the radius is 1, so that's going to be the hypotenuse of this triangle. It's going to be 1. All right, so if I keep going with angles, this angle at the top is a 90 degree angle, making a 90 degree angle with the positive x-axis. Okay, if I go 30 degrees beyond that, that puts me at 120. If I go 45 degrees beyond that, that puts me at 135. And if I go 60 degrees beyond that, that puts us at 150. Okay, and then all the way to the halfway point of the circle, an extra 90 degrees, that's going to be 180. Okay, and then we just continue like that. So another 30 degrees past 180 is 210. If I go 45 degrees past that 180, that's 225. 60 degrees past that 180, that is 240. 240, and if I go 90 degrees past that 180, that is 270. Okay, then let's go one more of these. So another 30 degrees puts us at 300. If I go 45 degrees past that 270, that puts us at 315. And going 60 degrees past that 270, that puts us at 330 degrees. Okay, so those are all of the nice angles measured in degrees along the unit circle. So now let's get all of those things in radians. Okay, so if I have 0 degrees, well, that's converting it to radians. That's also going to be 0 radians. And we've seen what 360 degrees is, a full circle. Well, that is 2 pi radians. 2 pi radians, that is a full circle. Okay. So that means the halfway point of the circle, 180, that's pi radians. And typically we don't write the units in radians. So now I'm going to get a little lazy. I'm going to stop writing the units. But that's usually the convention. In radians, we don't usually write the units. Okay. If I go half of that, so this was half of a circle. If I just go half of that, that's going to be halfway to pi, and that's going to be pi over 2. So this is where I'm going to start to use these fraction bars. This is pi over 2 radians. Okay, nice. So that's pi over 2. If I double that, it gets me to here, to pi. So doubling pi over 2 is 2 pi over 2. If I triple that, that takes me all the way to here. That's going to be 3 pi over 2. That is 3 pi over 2 in radians. 3 pi over 2 in radians. Okay, so now let's do all of our 45 degree angle type things. So pi over 2, that was the same thing as getting to 90 degrees. Well, 45 is getting halfway to 90. So that's getting halfway to pi over 2. If I divide pi over 2 by 2, I get pi over 4. That is pi over 4. Okay. So how can I get all of those like pi over 4 multiples? Well, if that's pi over 4, getting to the 90 where this is, well, that would be 2 pi over 4. But 2 pi over 4, that just simplifies to pi over 2. Okay, if I went, so this was going 1 pi over 4. Oops, sorry. Ooh, let's erase that. So getting from here to here, that was a pi over 4. And getting from there to there, that's another pi over 4, 2 pi over 4. And then getting from here to here, that would be 3 pi over 4. 3 pi over 4, let's label that. 3 pi over 4. And then getting from there to there, that's another pi over 4. This would be 4 pi over 4. But 4 pi over 4, that just simplifies to pi, so that's good. If I go another pi over 4, that puts me here. That would be 5 pi over 4. 5 pi over 4, that's the same thing as 225 degrees. If I go another pi over 4, that is 6 pi over 4, that's here. But 6 pi over 4, that's the same thing as 3 pi over 2. Okay, 6 pi over 4. If I go another pi over 4, another 45 degrees, that's here, 7 pi over 4. Okay, so that is 7 pi over 4. And if I go another pi over 4, gets us all the way around. That is 8 pi over 4. But that simplifies to 2 pi. That's good. That's good. So those were all the pi over 4 increments. All the pi over 4 increments. Okay. All right, so next up, I want to do all of these 30-degree increments. So all of these 30-degree increments. Okay, so I'm going to erase these kind of helper lines that I had out here. Okay. Okay, all right, so let's do all these 30-degree increments. So 90 degrees takes me here to pi over 2. Well, 30 degrees, to get to 30 degrees, I got to divide that by 3. So if I divide pi over 2 by 3, well, that would give me pi over 6. That would give me pi over 6. That would give me pi over 6. So pi over 6 is 30 degrees. So pi over 6 is 30 degrees. If I go another 30 degrees, that puts me over here. So this would be pi over 6. This would be 2 pi over 6 if I go another 30 degrees. Well, 2 pi over 6, that simplifies to pi over 3. So 2 pi over 6. So 60 degrees, that is pi over 3. If I go another pi over 6, that puts me here, 3 pi over 6. That simplifies to pi over 2. Now, if I go another pi over 6, another 30 degrees, that puts me at 4 pi over 6. And that simplifies to 2 pi over 3. All right, let's go another pi over 6, another 30 degrees. If I go another pi over 6, that puts me here at 5 pi over 6. That one doesn't simplify. So this is 5 pi over 6. Okay, almost halfway. So if I go another pi over 6, that is 6 pi over 6. That simplifies to pi, which is good. Nice. So let's go another pi over 6, another 30 degrees. That's 7 pi over 6. This one doesn't simplify, so 7 pi over 6, that is 210 degrees. All right, I think we saw that example in the last video. Another pi over 6, another 30 degrees, 8 pi over 6. 8 pi over 6, that simplifies to 4 pi over 3. 4 pi over 3. If I go another pi over 6, that is 9 pi over 6. 9 pi over 6, that simplifies to 3 pi over 2, which we already got. Nice. So another pi over 6, another 30 degrees, puts me at 10 pi over 6. And that simplifies to 5 pi over 3. A couple more to go to make it all the way around. Next one is an 11 pi over 6, going another 30 degrees. So that one doesn't simplify. That is just 11 pi over 6. And then finally, if I go one final pi over 6, that is 12 pi over 6. 12 pi over 6, and that does simplify to 2 pi. Okay, which is what we'd expect. Okay, so at this point, we have all of these angles in this unit circle, these nice angles measured in degrees as well as radians. Okay, so I'm going to erase some of these guide things that I had written here just to focus on now, well, what are the coordinates of these points? Okay. All right. Okay, because to evaluate our trig functions, we're going to need to know what are y and what are x. Okay, so all right, so let me start with these nice points on the x and y axes. All right, so I'm going to start. Let's put these in a different color. So right here, this point on the positive x-axis, well, that's 1 unit. That's 1 unit away from the origin. So that x-coordinate is 1, and the y-coordinate is 0. So that means in the opposite side, this would be -1 on the x-axis and 0 for y. So this point at the top would be 0 for the x-coordinate, 1 for the y-coordinate. And this point at the bottom, of the unit circle, well, that is 0 for x and -1 for y. Okay, so those are the easy ones to label. So what about all these other ones with these like 30 degrees or 60 degrees or 45 degrees and maybe in the other quadrants? How do we get those? So this is where we can use our 30, 60, 90, 45, 45, 90 triangles. So for this angle at the 30 degree, if I were to drop a perpendicular straight down, it's making a right angle like this. And I have a right triangle already drawn over here that matches that. Okay, so I have to just remember my side relationships in a 30, 60, 90. So if I know the hypotenuse is 1, the side opposite the 30, we get by dividing that by 2. Because that's going to be 1/2. That's going to be 1/2. You know what? Let me put that 1/2 in a different color. 1/2. That is 1/2. Okay, and if I know the side opposite 30, to get the side opposite 60, I multiply that one by square root of 3. So this side is going to be √3/2. So I can label those coordinates in my unit circle. Okay, so this length, this horizontal length, is my x-coordinate, √3/2, and that vertical length is my y-coordinate. My 1/2 is my y-coordinate. Nice. Okay, so that also means in the 60-degree angle, well, it'll get flipped. It'll get flipped because my triangle is going to get flipped. This 30, 60, 90 would switch the roles of that horizontal and that vertical length. So that means this x-coordinate is going to be 1/2, and the y-coordinate is going to be √3/2. Okay, so that's nice. I kind of get that one for free if I knew the 30-degree angle. So for my 45, let's remember our 45, 45, 90 side relationships. If I know the hypotenuse there, we divide that by square root of 2 to get the legs. So we divide by square root of 2 to get the legs. So that's going to give us 1/square root of 2, 1/square root of 2 for the legs. It's really common in the unit circle to rationalize the denominator though. So if I did that, I would multiply top and bottom by √2/2. Okay, so on the numerator, 1 times √2 is √2. On the bottom, √2 times itself is 2. Okay, so that's commonly how we'll see that written. So both the x-coordinate and the y-coordinate are the same. They are both √2/2. Same for the y, √2/2. Nice, and at this point we have all the coordinates in this first quadrant labeled. Okay, all right. So in fact, so now what I can do is, so there's a couple things I want to mention. So one is, let's quickly get all the remaining coordinates. So I can use that just by symmetry of the picture. And then I'm going to show you a shortcut for remembering these, a little memory trick for remembering these. Okay, all right, so the first thing to notice based on the symmetry of the picture, is that this 30-degree angle, it's kind of symmetric to this angle, this 150, because that's 30 degrees sort of up from 180. It's also symmetric to this one, where the 210 is, and it's symmetric to this one, where the 330 is. So the coordinates I would expect to share that symmetry. All right, so for this point over here, notice that the x-coordinate should be opposite. It should be negative. Let me zoom it in a little bit. This x-coordinate should be negative √3/2, and the y-coordinate is going to be the same. It's going to be 1/2. Nice. Whereas with this point, well, now both the x and the y are negative. So negative √3. Ooh, let's write that a little better. It's a little hard to fit this in. So negative √3/2, and then negative 1/2 for the y-coordinate. All right. And for this coordinate, the x-coordinate is positive √3/2, and the y is negative, negative 1/2. Awesome, awesome, awesome. So we got those. So we got those labeled. Let me, in fact, continue my highlight to include those points. All right, now let's do all the 45 ones. Okay, so the 45, here are the coordinates. Well, that kind of matches up, that's symmetric to this, where the 135 is. And in this quadrant, that matches where the 225 is. And in the fourth quadrant, that's symmetric to where this 315-degree angle is. All right, so in my second quadrant, the x is going to be negative. So I'll get negative root 2 over 2, but the y is positive, root 2 over 2. In this third quadrant, x is negative, root 2 over 2, and y is negative, negative root 2 over 2. In the fourth quadrant, x is positive, root 2 over 2, but y is negative, negative root 2 over 2. All right, so, and then finally we got these one remaining set of points. Okay, so where the 60 is, I had this coordinate, that's going to be mirroring where the 120 is. It's mirroring where this 240 is. And that's mirroring where this 300 is. All right, so in the second quadrant, I make the x be negative, negative 1/2. And the y stays the same, positive. In the third quadrant, x is negative, negative 1/2. And y is negative, negative root 3 over 2. In the fourth quadrant, x is positive, but y is negative. Okay, and that is all of the labeling in my unit circle. Okay. So the big things we need to be able to do this is we need to be able to get the angles. We need to be able to get all the angles, how we did initially. Of course, some of y'all may have the unit circle memorized. That's awesome. Some of y'all may be on your way to getting it memorized. That's also great. But if you're still practicing with it, remember, we can always kind of measure it out in increments like we saw earlier. And to get all of these coordinates, well, they just come from our 30, 60, 90, or 45, 45, 90 relationships. So if you know those relationships, getting those coordinates is quick. Okay. So I promised a shortcut for remembering these coordinates. Sort of like a memory trick. So here's the memory trick. All right. So this x coordinate right here is, I can think of this as square root of 0 over 2, this x coordinate. This next x coordinate going down is square root of 1 over 2. Because square root of 1 is just 1. I get 1/2. Well, the next one is square root of 2 over 2. And maybe you're seeing a pattern with the numerators now. Notice the numerator, I just keep increasing by 1, what's inside of the square root. So the next x coordinate is root 3 over 2. And this next x coordinate, if I kept that going, would be square root of 4 over 2. But square root of 4 is 2, so this simplifies to 1, which is what we have. And the same thing happens with the y coordinates, but in reverse. So this y coordinate is root 0 over 2. This y coordinate is root 1 over 2. This y coordinate is root 2 over 2. And so on. That pattern continues. So those y coordinate ones, let me just erase. Because the same pattern, just in reverse. Okay, but that's a trick we could use, a memory trick, for getting the coordinates in this first quadrant. And if you know the first quadrant, the other ones are easy, just based on the symmetry. You just got to think about, well, how does the sign change for x and y? Okay, all right, so let's do some examples. How do we use this unit circle? So in this first example, I want to find all trig functions of the angle 5 pi over 6. So I first just want to show you, well, how could I do this if I didn't remember my unit circle or didn't remember my coordinates? Okay, so I'm going to draw my axes. Because even if I don't remember my unit circle, if I know my 30, 60, 90, or 45, 45, 90 stuff, I can always use that to get it, even if I don't have the whole thing memorized. Okay, so what I do need to be able to do is get this in terms of degrees and know where it is in the unit circle. So we know that pi radians, is 180 degrees. And if you divide that by 6, you'll get 30. And multiply by 5, you'll get 150. So this is 150 degrees. Okay, so I'm measuring 150 degrees from the positive x-axis. That is going to be somewhere here. Measuring a 150 degree angle. 150 degree angle like this, which means that's the remaining angle over here. That is a 30 degree angle, which means if I drop a perpendicular, that's making a 60 degree angle up there. This is a unit circle, so I know this radius is 1. And if I know that radius is 1, well, the side opposite the 30, I divide it by 2, so 1/2. And to get the side opposite 60, I multiply that side by root 3. So that gives me root 3 over 2. Ah, nice. At this point, I got these coordinates. So this x-coordinate, well, the x-coordinate's got to be negative. It's negative root 3 over 2. And the y-coordinate is positive. It's just 1/2. And if we look at the unit circle, does that match what we got at that 150? Let me zoom it out a little bit. Yeah, it matches what we had at that 150. Okay, so nice. So again, I can get these even if I don't have the whole unit circle memorized. If I know my 30, 60, 90, or 45, 45, 90, as long as I can figure out where this angle is in the unit circle, I can get its coordinates very quickly. All right, so let's remember what sine, cosine, tangent are in the unit circle. Remember, sine is the y-coordinate, which for my point is just 1/2. And that's it. That is what sine, let me just write that 2 better, 1/2. That's what sine of 5 pi over 6 is. Cosine is the x-coordinate. And that is negative root 3 over 2. Okay, so now our trig functions can sometimes be negative. So that wasn't happening with SOHCAHTOA when my angle was between 0 and 90. But now, because my angle can be bigger in other quadrants, I can get negative outputs. Tangent is y over x, and the y-coordinate is 1/2. Divided by x is negative root 3 over 2. And if I simplify this, if I multiply it by the reciprocal at the bottom, I'll get negative 1 over root 3. Negative 1 over root 3. If I did want to rationalize the denominator, this is the same thing as negative root 3 over 3. Okay, the remaining trig functions, I just reciprocal these. So cosecant is the reciprocal of sine. That's going to be 2. Secant, I reciprocal the cosine, and I'll get negative 2 over root 3. Let me not worry about rationalizing the denominator. And then cotangent is reciprocal of tangent. That's going to be negative root 3. Negative root 3. Now we got them. We got all 6 trig functions. Okay, so let's do another example. Let's do another example which has several parts. So let's do a bunch of these. And for these other ones, I am going to practice just using the unit circle rather than, drawing a separate picture like this and figuring out what the coordinates are. We could definitely do that for all of these, but let's just practice using the unit circle if I have it as a tool already. It'll make it quicker. So I know secant is 1 over cosine, and cosine is x. So 1 over x. So I'll get 1 over, and let's look at where 4 pi over 3 is in the unit circle. So 4 pi over 3 is here, and I need the x-coordinate, which is negative 1/2. So the x-coordinate at that point is negative 1/2. So dividing by that fraction means multiply by the reciprocal. That gives me negative 2. And that's it. Okay, let's do cotangent of 3 pi over 2. I know cotangent is the reciprocal of tangent. So that's x over y. And let's look at where 3 pi over 2 is in the unit circle. So that's this bottom point. So x over y. So my x-coordinate, let's zoom it out a little bit. The x-coordinate is 0 there. Y is negative 1. Oh, that just becomes 0. Nice. Okay, part C. Now what if I had tangent of that angle? So tangent is y over x. So that's going to reciprocal what I just had. So I'll get negative 1 on top. That's y. Divided by x is 0. Oh, but that's undefined. I can't divide by 0. That is undefined. Ooh, okay, so sometimes trig functions can be undefined. That can definitely happen in the unit circle because I'll get a fraction for a bunch of these trig functions. And if the bottom is 0, it would lead to it being undefined. All right, so let's do a tougher one. And that's where I'll end this video. What if I have cosine of 19 pi over 6? Cosine of the angle 19 pi over 6. So the first thing to notice is, wait, 19 pi over 6, my circle doesn't go up to that. Like I see 11 pi over 6, but it doesn't kind of go beyond that in terms of these pi over 6s. So how do we do that? How do we do that if our angle is kind of bigger than anything that I see on the unit circle? So what I can do is I can draw a picture. I'll draw my axes, and then I'll draw my circle. I'll draw my circle. I'll draw my circle. Okay, so we got this. So the key thing to keep in mind is that, if our angle is kind of bigger than what we'd expect to be from going around one full time around the circle, we keep going beyond that point. So like I know the starting point over here is where the angle is 0, and it's also where the angle's 2 pi. And if I get a common denominator with the 2 pi and multiply it by 6 over 6, multiply that by 6 over 6, I'll get 12 pi over 6. And in fact, in the unit circle, we saw that if you go 30 degrees before that, well, that was 11 pi over 6. That was 11 pi over 6. Okay, and if we keep measuring these increments of pi over 6, so if I went another pi over 6 past 11 pi over 6, that's at 12 pi over 6. If I go another pi over 6 past 12 pi over 6, well, that's 13 pi over 6. Okay, in my unit circle, that was kind of at the same spot. It was kind of at the same spot as pi over 6. Pi over 6 was at the same spot. At the same spot as 13 pi over 6. So it's not that they're the same angle. They're definitely not the same number, pi over 6 and 13 pi over 6. They just happen to be in the same spot on the unit circle. Okay, so if I keep going these increments of pi over 6, well, the next one would be, that just looks a little too far. The next one would be at 14 pi over 6. I got to get to 19 pi over 6, so let's go another one. That would put me at 15 pi over 6. That's another 30 degrees. Let's go another pi over 6, another 30 degrees. That is 16 pi over 6. Let's go another 30. That is 17 pi over 6. Let's go another 30. That puts me at this 180 mark, 18 pi over 6. Okay, and then we got to go one more beyond that, another 30 beyond that to get to 19 pi over 6. So, well, what is that at the same spot as in my unit circle? So if I look up, going 30 degrees past the 180, well, that's 210, or 7 pi over 6. So this is at the same spot as 7 pi over 6. So I need the coordinates for 7 pi over 6. Okay, so I'm going to use those. Cosine, I know, is my x coordinate. And if I look at my unit circle to see, well, what were the coordinates of x where 7 pi over 6 is? Well, it's just negative root 3 over 2. That is negative root 3 over 2. And that is my answer. Okay, so next time we'll see, well, how can I do stuff like this? How can I figure out trig functions evaluated at negative angles? Turns out it's very similar to stuff that we've seen here.